Hi again. I hope you had a chance to have a look at that problem that I gave you. And did you also think about what kind of logic gate that might be? Anyway, let's go ahead and work the problem together. We'll draw a little truth table here. So what we have is A, B, and Y. All right. Let's look at the first condition. We'll have A as 0, B as 0, and we'll try to determine what Y is. So we're going to make A as 0 here, and we're going to make B as 0 over here. All right, 0 to this NMOS does what? It means that this is in an open condition. 0 to this PMOS means that this basically is in a closed condition. Okay. B, 0 to this gate here, this NMOS gate, means that this is really also in an open condition. And a 0 over to this PMOS gate means that this is really in a closed condition. So let's look at how Y is connected. Y, there's no pathway to ground here, no pathway to ground here. But if I look this way, closed switch, Y then indeed is connected to 5 volts or logic level 1. Okay, that's our first case. All right. Now, let's look at the case where we've got A as 0 and B a 1. Okay, so A is a 0, which means that that's still in an open condition, and this guy's still in a closed condition, but now we're having B being a 1. A 1 to this NMOS device means that this is what? This becomes a closed switch, so that's closed. A 1 connected to this guy, this PMOS, means that this guy now moves into an open condition. Okay, so let's look at how Y is connected. So Y cannot connect to 5 volts because this PMOS has become an open switch. However, looking this way, I've got a closed switch condition here, and so Y is connected to ground, to 0, through that particular transistor. And so the output over here then is a 0. Okay, the next condition. Let's now say that we've got A a 1 and we've got B a 0. So I'm just going to circle the condition for B, 0. A 0 means that this transistor over here does what? Well, it becomes an open switch. Okay, a 0 to this guy over here means that this becomes what? This becomes a closed switch over here. Okay, all right, looking this way. A 1 basically connected to A means what? It means that this becomes an open condition, and a 1 connected to this guy over here means that this becomes a closed switch, like so. So let's look at how Y is connected. Well, we have no pathway here because this is really in an open state. This is closed, but then this is now open. This transistor is open, so there's no pathway to 5 volts. Coming across here, this is now a closed switch, and we have a connection really to ground. And so for the case where we've got A a 1 and B a 0, then this would also be a 0. All right, let's look at the final case where A is a 1 and B is a 1. Okay, so A is a 1, I'm circling the condition here, and B is a 1 here. What does this do? A 1 to this transistor means that this NMOS is now in a closed condition. A 1 to this NMOS transistor here means that this is in a closed condition. However, the 1 connected to this guy means that this is open, and the 1 connected to this guy means that this is an open. And so our pathway for Y is clearly connected to 0 or ground, and so the logic level for Y is a 0. Now, what you might do is you might recognize this as a particular kind of gate, and it is in fact a NOR gate. Okay, here once again I'm actually showing you an NMOS device. Now, people often talk about gate length, and I just want to quickly explain what we mean by gate length. The gate length is really the distance between this active region of the drain and the active region of the source. And so it is really this dimension here that we refer to as the gate length. Now, if we're operating this device, let's say as we've already considered, where we're looking at voltages of 5 volts and 0 volts, then this gate length over here has to be typically, I would say L being 1 micrometer or greater, okay? Now, today at the very high end, we are considering these gate lengths to be very, very small. In fact, we might be considering gate lengths of the order of really 20 nanometers. That's very small. And typically in some of these integrated circuits, we can have billions of transistors, and I mean billions of transistors. But if we have a very, very small gate length, let's say of the order of this, then if we were to apply 5 volts between drain and source, well, this would just be simply shorted out very quickly. So as we go to smaller gate lengths, then really the voltages that we use for these logic devices have to become less and less. And so we're typically talking about voltages of now less than 1 volt. I hope all of this has given you a little bit of an understanding of CMOS circuits and how they're actually used to construct logic gates. Look, take it easy, and I'll see you next time.